Our universe is vast. Billions of stars swirl in our galaxy, the Milky Way, and there are billions of galaxies out there. We look up at night and see those distant points of light. For millennia, humans have dreamed of reaching them. Our own solar system is remarkable, full of wonders from the rings of Saturn to the plains of Mars. But it is just our cosmic backyard, a tiny speck in an immense ocean of stars and possibilities. The desire to explore beyond is deeply human. So what if we could travel faster than light? This is the dream of FTL travel. It means crossing the immense gulfs between stars, not in thousands of years but in months, weeks, or even days. Imagine stepping onto a ship and setting a course for Alpha Centauri, our nearest stellar neighbor, arriving there within a human lifetime. This isn't just a staple of science fiction stories, it is a profound question for science and for humanity. Could we ever break this ultimate speed barrier? Could we truly become starfarers? The allure of faster-than-light travel is powerful. It promises a universe unveiled. Think of the new worlds we could discover, planets orbiting other suns, perhaps teeming with life. We could search for answers to our biggest questions. Are we alone in the cosmos? What is our ultimate destiny? FTL travel wouldn't just be a technological leap, it would be a transformation of our understanding. It would change everything about our place in the universe. But the scale of this challenge is monumental. Light travels incredibly fast, about 300,000 kilometers every single second. Yet, even at this astonishing speed, light takes over 4 years to reach Proxima Centauri. To cross our own Milky Way galaxy, that takes light 100,000 years. Faster than light travel isn't just about building a faster engine. It's about finding a new way to traverse the cosmos. It's a dream worth pursuing. There is a very big hurdle to this dream, a fundamental law of physics from Albert Einstein. His theory of special relativity, published in 1905, revealed a cosmic speed limit, the speed of light in a vacuum. According to this theory, nothing with mass can ever reach this speed, let alone exceed it. This isn't just a suggestion, it's a core principle of how the universe works. It has been tested and confirmed countless times. It stands as a formidable barrier to our interstellar ambitions. Why does this speed limit exist? Einstein showed us something remarkable. As an object with mass accelerates, its mass effectively increases. The faster it goes, the heavier it gets. Approaching the speed of light, its mass would become infinite. To accelerate an infinite mass, you would need an infinite amount of energy. This is simply not possible. The universe has rules, and this is one of its most fundamental. It's a beautiful, elegant piece of physics, but it's also a deeply frustrating one for aspiring star voyagers. Even if we could build ships that travel at, say, 10% the speed of light, it would still take over 40 years to reach the nearest star system. Journeys to other parts of our galaxy would take millennia. Generations would live and die aboard such a ship. The universe, for the most part, would remain silent and out of reach. This limit isn't just an engineering problem, it is woven into the very fabric of space-time. To challenge this limit means we need to rethink our most basic understanding of physics. It's a monumental task, but humanity has always been drawn to monumental tasks, especially those that promise the stars. So, if we cannot break the speed of light directly, are there other ways? Perhaps. Physics is a wonderfully creative field. Scientists love to explore the edges of what's known. They look for loopholes, theoretical possibilities that might, just might, allow us to sidestep Einstein's Great Barrier. Not by accelerating an object through space faster than light, but by finding clever ways to manipulate space-time itself. This is where the ideas become truly mind-bending and exciting for the future of exploration. One such idea is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. Imagine a spacecraft enclosed in a bubble of space-time. This bubble would contract space-time in front of the ship and expand space-time behind it. The ship itself wouldn't be moving through space at incredible speeds. It would remain stationary within its local bubble. But the bubble itself, and the ship within it, could be propelled forward, effectively surfing on a wave of space-time. This could, in theory, allow for travel faster than light without violating relativity locally. Another fascinating concept is the wormhole, also known as an Einstein-Rosen bridge. Think of space-time as a giant sheet of paper. Two distant points on that paper could be connected by a long line, or you could fold the paper and punch a hole through it, creating a much shorter path. A wormhole is a theoretical tunnel, a shortcut through space-time. It could connect vastly distant regions of the universe. Imagine stepping into a wormhole here and emerging light years away, almost instantaneously. These concepts are, of course, highly speculative. They exist primarily in equations and theories. The Alcubierre drive, for instance, would require something called exotic matter, matter with negative mass energy density. We have never observed such matter, and we don't know if it can exist. Wormholes, if they exist, might be incredibly unstable or microscopic. The energy requirements for both could be astronomical, far beyond anything we can currently imagine. But these ideas stretch our minds. They encourage us to ask, what if? And that is always the first step. The journey to develop such a capability, even if it takes centuries, would push the boundaries of science. It fuels our curiosity and inspires us to learn more about the universe we inhabit. Let us imagine for a moment. Imagine that one day we achieve faster-than-light travel. The entire Milky Way galaxy would open up before us. Its stars and planets, no longer distant lights but destinations. A new vast frontier would beckon. An entirely new era for human civilization would begin. Exploration on an unimaginable scale. We could visit, study, and even live on new worlds. A cosmic destiny, a natural progression for humanity. Achieving faster-than-light travel would transform more than just our physical reach. It would fundamentally alter our perspective, our understanding of the universe, and crucially, our understanding of ourselves, our place within this vast, intricate cosmos. We would transition from being a species bound to a single planet to becoming true citizens of the galaxy. This shift in identity would be profound. It would echo through every aspect of human culture, art, and philosophy for generations. We would become a truly galactic species, part of a much larger cosmic neighborhood. Perhaps we would find it teeming with other intelligent civilizations. Imagine the exchange of knowledge, culture, and ideas. Or perhaps we would find the galaxy to be silent, vast, and empty, awaiting pioneers. Either discovery would be equally momentous. It would define our role in the universe. Are we one voice among many? Or are we the first to venture forth into the great unknown on this scale? The answer lies out there. The philosophical implications are immense. What does it mean to be human when our species is scattered across light years, across diverse worlds with different skies, different suns? New cultures would undoubtedly arise, shaped by new environments and experiences. Yet a common thread of humanity would persist. The challenges of interstellar governance, communication, and identity would be immense. But they would also drive innovation and new ways of thinking about society and our shared future. The universe awaits.